Hi, my name is Brett Threlkill, and I'm the Applications Manager at Advanced Illumination. I want to welcome you to my fourth and final presentation in this series for Mastering Machine Vision Inspection, and to take a few minutes to talk about the fourth cornerstone of machine vision illumination. The four cornerstone concept was devised as a teaching tool for labeling and demonstrating four methods that can be applied to enhance or create appropriate image contrast of parts versus their backgrounds. The four cornerstones consist of geometry, pattern and structure, filtering, and wavelength. Of those four cornerstones, the pattern and structure are based solely on the design, construction, and working distance of the light, and they provide options that the other cornerstones do not. The ultimate goal in understanding the four cornerstones is to have effective, consistent, and robust features best suited for a given inspection. A frequently asked question concerning the four cornerstones concept is priority of investigation. For example, is wavelength more important than geometry? Should we first be starting with structure? And when do we apply filtering? There's really not an easy answer to that question. The steps you take will depend on the part and the expected application-specific results. The geometry and structure are more important when dealing with specular surfaces, whereas wavelength and filtering are more crucial for color and transparency applications. Understanding how manipulating and enhancing the image contrast from a part against its immediate background using the four cornerstones is crucial for assessing the quality and robustness of the lighting system. Of course, it's not uncommon to find that more than one cornerstone is required to solve an application. Pattern lighting is a technique in machine vision where a known pattern of light is projected onto an object or scene. The way the pattern is deformed on the object's surface reveals information about its 3D shape. A camera captures the deformed pattern, and this information can then be used to reconstruct a 3D model of the object. Software algorithms analyze the captured pattern and extract the 3D information. This style of LED pattern lighting was designed as a cost-effective and safe alternative to laser lighting. The use of pattern lighting can offer various solutions to different types of applications. 3D object scanning and reconstruction is the most common application, used in robotics, manufacturing, and quality control. Facial recognition uses structured light to project patterns onto faces to capture accurate 3D models for biometric identification. For gesture recognition, patterns are projected onto the hands or other body parts, or pattern light can be used to track and interpret gestures. And for visual inspection, pattern light can be used to detect defects on surfaces in manufacturing and quality control applications. The advantages of using structured lighting include high accuracy. Structured light can produce high-resolution 3D models with accuracy in millimeter range. The technique is non-contact and does not harm the object being scanned. Pattern light can be used on a wide variety of materials, including reflective and textured surfaces. However, there are some limitations. The accuracy of pattern light can be affected by ambient light conditions. Analyzing the captured patterns can be computationally intensive and expensive. Projectors and cameras need to be carefully calibrated for accurate results. Pattern and structured lighting take on a whole new meaning when you take geometry into account. It should be noted that working distance is an important element of geometry and structured lighting. For example, this bar light at 50 millimeter working distance produces a predictable image which matches the shape of the light. As the working distance is increased, the pattern of the light begins to change. At 300 millimeters, this 12-inch bar light resembles a spotlight pattern more than that of a linear array. And finally, at 600 millimeters, the shape of the light is that of a spotlight. This phenomenon can be attributed to the combination of light divergence, the inverse square law, and lens cone overlap. To understand the need for structured line lighting, we must first understand the difference between area scan cameras and line scan cameras. Images from area scan cameras are the most familiar because of photography, television, webcams, and other similar devices. An area camera consists of a two-dimensional array of pixels with multiple rows and columns. Line scan cameras were developed for high-resolution imaging of large, continuous objects that wouldn't fit within the frame of a traditional area scan camera. Images from line scan cameras consist of only one row of pixels, A two-dimensional image is created by moving the part under the camera or the camera over the part. The generally accepted characteristic of line scan imaging is that it needs higher illuminance than an area scan camera. Whereas lighting for an area scan camera can be strobe for increased power, line scan cameras take a continuous image, thereby requiring a higher light intensity. It's very difficult to optically focus light into a thin line. Most commercial line light sources focus a row of LEDs into a line using a cylindrical lens. Line lights represent a growing application role within the machine vision lighting market. Most line lights employ a rod lens or Fresnel lens to produce a focused line. They are primarily utilized in moving web applications where continuous inspection is required in conjunction with a line scan camera. The primary benefit of a focused line light is that it produces a much higher radiant power in a narrow line that is often needed for the high web speeds associated with applications such as textiles, steel surface defect detecting, and label inspections. This provides the intensity required to eliminate image blur, compensating for the short exposure times and high line rates. As the material runs down the assembly line, the focus of the beam is determined by the power output of the light working distance from the material, and the lens chosen for the application. Rod lenses play a crucial role in shaping the light emitted by the line lights, offering unique properties that enhance their functionality. The lens acts like a tiny cylindrical magnifying glass, focusing light in one direction. When light from the source hits the rod lens, it gets focused into a much thinner line, creating a sharper and more intense beam. Benefits of using rod lenses include a sharper light line, increased brightness, and adjustable beam control. By installing different rod lenses, the shape of the line of the light can be changed, offering flexibility in illuminating specific areas and the use of different working distances. These images were all taken with the same 12-inch line light. The focal length and diameter of the rod lens determine the beam width and intensity of the light, depending on the working distance. Careful alignment of the rod lens and light source is crucial for achieving optimal results. The LL158 oblique line light produces an oblique 30-degree line of illumination for line scan applications. When oriented across a moving web or conveyor line, unlike standard line lights, this linear light's unique geometry highlights engraved or raised lines that run parallel to the material's travel. Another type of directional front lighting is this coaxial light, which incorporates a beam splitter and is used to manipulate and direct the light. Beam splitters are typically thin glass plates or prisms coated with specialized reflective layers. They intercept an incoming light beam and split it into two. Overall, beam splitters are valuable tools in machine vision, offering diverse functionalities for light manipulation and enhancing the capabilities of various imaging and inspection systems. Coaxial light provides a type of diffuse illumination generated from an internal source. The light is then directed downward into the imaging plane via 50% beam splitter, while 50% of the light passes through and becomes absorbed or scattered light. The reflected light is then collected by the camera. This is ideal for imaging highly reflective objects or where the area of inspection is obscured by shadows from its surroundings. In this first image taken with a DL225 coaxial light, the sealing surface of the water bottle is clean and unblemished. In the second image, the large gouge is easily seen, as are the much smaller flaws. Whether your application calls for structured lighting, pattern lighting, or lights designed specifically for area scan applications, the various designs of the lights offer powerful techniques with a wide range of benefits for machine vision applications. Their accuracy, versatility, and non-contact nature make them a valuable tool for various industries. Especially, and this cannot be emphasized strongly enough, when you plan your application around the machine vision lighting. Taking into account your working distance, field of view, your inspection goals, you can then plan your type and geometry of lighting, the style of camera required, and the focal length of the lens. Combined, these techniques and components will make your application effective, consistent, and robust. My father started AI in his garage over 30 years ago, and we were the first machine vision LED lighting company in existence. As such, we pride ourselves on being a full customer support company. If you need assistance with an ongoing or a future application, please don't hesitate to reach out to me. I would also encourage you to download our practical guide to machine vision lighting. This comprehensive handbook covers everything I talked about today and much more. If you're looking to get into machine vision lighting industry or would like to refresh principles that you learned in the past, this industry-leading lighting guide is the best place to start. Thank you for your time.